So today we're going to be solving May-June 2023 paper 21. Okay, that's paper 2 variant 1. May-June 2023 paper 2 variant 1. So here we have question number 1, which says tellurium is an element in group 16. The most common isotope of tellurium is tellurium 130. Its electronic configuration is krypton 4d10 5s2 5p4. Part A says complete table 1.1. The nucleon number is just the mass number, right? That's just 130, right? That's written over here. So that's written over here, 130. Okay. What's the number of neutrons? Well, we have to first look at the proton number. So tellurium, they've said, is in group 16, right? So if you look at group 16, here's tellurium. Okay. The atomic number is 52. So the atomic number is 52. So that's the number of protons, right? That's the number of protons. Remember the nucleon number? The nucleon number is protons plus neutrons, right? Protons plus neutrons. So this is protons plus neutrons. We know that the atomic number is 52. So that means that the number of neutrons is 130 minus 52, which comes out to 78, right? Which comes out to 78. So that's the number of neutrons. The number of neutrons is 78. The number of electrons is equal to the number of protons because it's a neutral atom. So the number of electrons is 52. Identify the subshell in an atom of tellurium that contains electrons with the lowest energy. So the lowest energy subshell is the 1s subshell, okay? And the highest energy subshell is the 5p subshell, okay? Again, the lowest energy subshell, right? The lowest energy electrons are the ones closest to the nucleus, okay? They're the ones closest to the nucleus. Construct an equation to represent the first ionization energy of tellurium. The first ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. Okay, so this is the equation for the first ionization energy. The radius of tellurium ions decreases after each successive ionization. State 2 factors that are responsible for the increase in the first 6 ionization energies of tellurium. Now they've told us that tellurium has the configuration krypton 4d10 5s2 and then 5p4, right? We're talking about the first 6 ionization energies. We're talking about the outer 6 electrons, which are these guys, right? We're going to focus on those. We have 5s2. Okay, so we have the 5s, and then we have the 5p4, right? We have the 5p4. So 5s2, 5p4, right? Those are the electrons in the fifth shell. Okay. Now the first electron we're going to remove is going to be this paired electron. It is going to be this paired electron. This is going to be the easiest to remove. Why? Because it's experiencing spin pair repulsion, right? We have a pair of electrons in the same p orbital, right? In the same p orbital. So that will be the first electron that's removed, right? The paired electron. So we can say that the second ionization energy is greater than the first ionization energy, right? Because the first electron removed, right? The first electron removed experiences spin pair repulsion, okay? Experiences spin pair repulsion. Experiences spin pair repulsion. Now let's say we remove the first electron, right? The next electron will be harder to remove, okay? The next electron will be harder to remove. Why? Because you have fewer electrons, okay? You have fewer electrons. So now they're repelling each other lesser, okay? You have fewer electrons in the outer shell, so they're repelling each other lesser, right? They're repelling each other lesser. So you can say as the number of electrons decreases, right? The number of electrons decreases, right? The electrons repel each other lesser, okay? Repel each other lesser, right? And therefore are more difficult to remove. And then lastly, once you remove the 5p electrons, right? Once you remove the electrons in the 5p subshell, then the electrons are harder to remove from the 5s subshell. So that's another factor that explains the increase, in the first 6 ionization energies, right? So another factor over here is that you're going to see an increase, okay? You're going to see a specific increase from the 4th to the 5th ionization energy, okay, an increase from the 4th to the 5th ionization energy, okay, due to an electron, due to the 5th electron being removed, okay, from the 5s orbital, okay, 5s orbital. So that means you have lesser shielding, right? That means you have lesser shielding. Okay, I'm just going to write this down here. Okay, so these are all different factors that explain the increase in the first 6 ionization energies, right? It can be increased by the fact that you have spin pair repulsion, so the first electron is generally easier to remove, right? The next electron will be harder to remove because you have no spin pair repulsion. In a more general sense, if you have fewer electrons in the 5th shell, there's fewer electrons in the same shell, so there's lesser repulsion between the electrons, so they're happier, okay, to remain in that shell, so it's harder to remove. And then you also see an increase from the 4th to the 5th because you're removing an electron from the 5s orbital, right? So that 5s orbital is closer to the nucleus, and there's lesser shielding, okay? And all of these factors, okay, will result in an increase in nuclear attraction, okay? They love seeing this, okay, an increase in nuclear attraction as a key point in any of these, okay, in any of these explanations, okay. For this 2 marks, this should suffice, but as I said, whenever a question like this comes, you should give the most detailed explanation possible, okay. You give the most detailed explanation possible, okay. So sometimes the points aren't necessarily, you don't necessarily get a mark for every point that you write, okay. In some cases, they'll give you a single mark for stating 2 different things, so they'll be like, you know, you get 1 mark for stating this and this, right? So you can never be sure. So always give the most detailed explanation possible. Sketch a graph in figure 1.1 to show the trend in the first 7 ionization energies of tellurium. Okay, so tellurium again is krypton, okay, and then 4d10, and then 5s2, and then 5p4. So the first 4 electrons are relatively easy to remove, right? You will see a slight increase from the 4th to the 5th, a slight jump. Okay, it's not a very big jump, just a slight jump because you're going from the P subshell to the S subshell. Okay, you're going from the P subshell to the S subshell. So this will be slightly higher than the general trend. Okay, and then the 6th electron. Now you removed all 6 valence electrons. You're going to see a big jump from the 6th to the 7th ionization energy. Okay, you're going to see a big jump from the 6th to the 7th ionization energy. So this is the general trend. Okay, there's a general increase for the first 4. There's a slight jump from the 4th to the 5th because you're going from the P subshell to the S subshell, and then you remove the 5th and the 6th electron from the S subshell, and there's a big jump from the 6th to the 7th because it has 6 valence electrons. This big jump over here shows that we have 6 valence electrons. Okay, the first 6 were relatively easy to remove. The 7th one is much harder to remove. Tellurium reacts with fluorine at 150 degrees Celsius to form TeFX. Molecules of TeFX are octahedral with bond angles of 90 degrees. Explain why TeFX has octahedral bond angles of 90 degrees. So when we have an octahedral shape, right, that means that the central atom is bonded to 6 other atoms. Okay, it's bonded to 6 other atoms. So this must be TeF6. Okay. So if we had to explain why it's octahedral with bond angles of 90 degrees, well, the first thing is that we can say that the tellurium, okay, is bonded to 6 fluorine atoms. Okay, tellurium is bonded to 6 fluorine atoms, and these bonds, okay, or more specifically these bond pairs of electrons, okay, these bond pairs of electrons repel each other equally, right? Repel each other equally. Okay, so this explains why they're all evenly spread out, right? All the bond angles are 90 degrees. Okay, so if you have 6 bonds and you want to spread them equally, the shape that you get is an octahedral shape, okay, with bond angles of 90 degrees. TeFX reacts with water to form tellurium hydroxide and HF. The oxidation number of tellurium does not change during this reaction. Construct an equation for the reaction of TeFX with water. Now I know that TeFX is just TeF6, okay, it's TeF6. It reacts with H2O, okay, We know that over here tellurium is +6, right? Because fluorine is -1 and we have 6 of those, right? Fluorine is -1 and we have 6 of those, right? Fluorine is always -1. We have 6 of those, right? So that means that over here tellurium must be +6, and then we get tellurium hydroxide, which is TeOH6, right? Again, oxidation number of tellurium remains +6, hydroxide is -1. We have TeOH6 and we get HF. Okay, we get HF. To balance this, we have 6 fluorines here. We're going to have 6 HF. And now we have 6 plus 6, that's 12 hydrogens. So we're going to have 6 H2O. Okay, and the equation is balanced. Name the type of reaction that occurs when TeFX reacts with water. Well, we have a covalent fluoride, right? We have a covalent fluoride reacting with water. This is similar to when a covalent chloride reacts with water, right? What happens is that the TeF bond is broken, right? This is called hydrolysis. Okay, this is called hydrolysis. This is similar to what you get with chlorides of period 3, right? Like when we have something like PCl5 or we have something like SiCl4, right? Non-metal chlorides undergo hydrolysis, right? The same idea here. Whenever you have a covalent fluoride or a covalent chloride, okay, you're going to have a hydrolysis reaction with water. Okay, this is what results in the formation of an acidic solution. Here we have question number 2, which says a neutralization reaction occurs when sodium hydroxide is added to sulfuric acid. They're given the equation for this neutralization. Part A says define the enthalpy change of neutralization. It is the enthalpy change. It is the enthalpy change when an acid, okay, when an acid and an alkali react. Okay, it's the enthalpy change when an acid and an alkali react. Okay, to form 1 mole of water. Okay, to form 1 mole of water. To form 1 mole of water. So the enthalpy change of neutralization is specifically for a neutralization reaction per mole of water formed. Okay, per mole of water formed. When an acid and an alkali react. Okay, it's the enthalpy change per mole of water formed. An experiment is carried out to calculate the enthalpy change of neutralization for the reaction between aqueous sodium hydroxide and sulfuric acid. 100 cm cube of 1 mole per dm cube sodium hydroxide is added to 75 centimeter cube. Okay, is added to 75 centimeter cube of 1 mole per dm cube sulfuric acid in a polystyrene cup. So we mix the sodium hydroxide and sulfuric acid, right, resulting in a neutralization reaction. We stir it. Okay, the results from the experiment are shown in table 2.1. Use equation 1 to calculate the amount in moles of sulfuric acid that is neutralized in the experiment. Now, in this particular experiment, right, we have this equation. So let me write this down. So let me take this from here. Right, we have this equation for the neutralization reaction between sulfuric acid and aqueous. Over here, let's first calculate the number of moles of sodium hydroxide and the number of moles of sulfuric acid, right? Number of moles of sulfuric acid is the concentration times the volume. The concentration is 1. The volume is 75 over 1000, right, in decimeter cube. So we get 0.075 moles of sulfuric acid. Okay, we have 0.075 moles of sulfuric acid. Okay, and then for sodium hydroxide, we have again the number of moles is concentration times volume. That's 1 times 100 over 1000. So that's 0.1 moles of sodium hydroxide, right? 0.1 moles of sodium hydroxide. Now here, sodium hydroxide is the limiting reactant. Okay, sodium hydroxide is a limiting reactant. Why? Because if we have 1 mole of sodium hydroxide, okay, if you have 1 mole of sodium hydroxide, only half a mole of sulfuric acid will react. Okay, again, because 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid. 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid. We have a 2 to 1 ratio. If we have 1 mole of sodium hydroxide, half a mole of sulfuric acid will react, or if we have 0.1 moles of sodium hydroxide, if we have 0.1 moles of sodium hydroxide, that will be 0.05 moles, right? So that's the number of moles of sulfuric acid that will actually react. That means sulfuric acid is in excess. The number of moles of sulfuric acid, that actually are neutralized in this reaction is 0.05 moles. Okay, 0.05 moles. Calculate the enthalpy change of neutralization using the results in table 2.1. Include units in your answer. Okay, So over here they've given us the initial temperature of the aqueous sodium hydroxide, the initial temperature of the sulfuric acid, and the final temperature, right? That's the maximum temperature of the mixture. So over here, when we mix these two solutions, our initial temperature is 20 degrees Celsius, our final temperature is 27.8 degrees Celsius, which means that delta T is 7.8, okay? Delta T is 7.8. In this particular reaction, we're mixing 100 cm cube of aqueous sodium hydroxide with 75 cm cube of aqueous sulfuric acid, right? So we're mixing 100 cm cube of sodium hydroxide. Okay, we're mixing 100 cm cube of sodium hydroxide, okay, plus 75 centimeter cube of sulfuric acid. So our final solution is 175 cm cube. The final solution is 175 cm cube, okay. We can assume that the final solution, right, 1 cm cube of the final solution has a mass of 1 gram. Then we can say that our M, okay, our M over here is 175 grams, okay. Our M is 175 grams, okay. And then the specific heat capacity is just 4.18 joules per gram per Kelvin, right? We're assuming that we have pure water at the end, essentially, okay. So then we can say Q is equal to MC delta T, okay, Q is equal to MC delta T, okay. Q is equal to 175 grams. That's the amount of water or amount of solution. Specific heat capacity is 4.18. The change in temperature is 7.8. Okay, so we get Q as 5,705.7 joules. Okay, 5,705.7 joules. Okay, we're going to find the enthalpy change of neutralization in kilojoules per mole. You can find it in joules per mole as well. Okay, but I'm just going to go with the usual units. So then this is equal to 5.7057 kilojoules, right? Now this enthalpy change, okay, this enthalpy change is for 0.1 moles of water formed, right? 0.1 moles of water. Again, we have 0.05 moles of sulfuric acid reacting. We're going to have double the moles of water, right? We're going to have double the moles of water, right? 0.1 moles of sodium hydroxide reacts, right? We get the same number of moles of water. So we get 0.1 moles of water. We want to find the enthalpy change per mole of water, right? So we can say that delta H is equal to negative Q over N, right? Where N is the number of moles of water and delta H is the enthalpy change of neutralization, right? Enthalpy change of neutralization. So this is negative 5.7057 divided by 0.1. So what we get here is negative 57.1 or negative 57.057 kilojoules per mole, okay? Negative 57.057 kilojoules per mole. The three significant figures, that's negative 57.1 kilojoules per mole. Right, now again, if Q is positive, right, that means that the reaction itself is releasing heat, right? It's an exothermic reaction. So we have an increase in temperature in the surrounding water. Q is positive, that means delta H is negative. If it's exothermic, it's heating up the surroundings, but the reaction itself is releasing energy. And since we want it per mole of water, we have to divide by the number of moles of water. Okay, that gives us the enthalpy change per mole of water. So we take negative Q and then divide by the number of moles of water. Complete the equation for the reaction that occurs when a solution of barium hydroxide is added to aqueous sulfuric acid. Include state symbols. So when barium hydroxide reacts with sulfuric acid, we get barium sulfate. Here we get barium sulfate and we get H2O. First, going to balance this equation, right? So to balance this, we're going to have 2H2O. Okay, we're going to have 2H2O, and then 1 of sulfuric acid and 1 of barium hydroxide, right? We have 2H plus and 2OH minus, so we get 2H2O, and then Ba2 plus and SO4 2 minus give us barium sulfate. We know that barium sulfate is insoluble, so that will be a solid, and H2O will be a liquid. Suggest why the enthalpy change of neutralization cannot be determined using the addition of dilute sulfuric acid to aqueous barium hydroxide. The reason this doesn't work, okay, the same way to determine the enthalpy change of neutralization as a reaction of sulfuric acid with sodium hydroxide is because you're getting a precipitate of barium sulfate. Okay, so we have two different reactions taking place. We have a neutralization and we have a precipitation reaction taking place. Okay, we have neutralization and a precipitation reaction taking place. In the case of sodium sulfate, we were making Na2SO4, but that was aqueous. So the sodium and sulfate ions remained in aqueous solution. They remained in aqueous solution. They were spectator ions. Okay, they were spectator ions. In this particular case, because you have a precipitation reaction, the enthalpy change that you're going to measure will be for both the neutralization and the precipitation. So you can't just determine the neutralization. Okay, so what we'll say over here is that there is an enthalpy change. Okay, there's an enthalpy change associated with, okay, it's associated with the precipitation, okay, with the precipitation of barium sulfate, okay, with the precipitation of barium sulfate. Okay, therefore the enthalpy change of neutralization cannot be determined. Okay, cannot be determined. So here we have question number 3, which says chlorine is a very reactive element. Chlorine reacts with silicon to form silicon 4 chloride. Describe the appearance of silicon 4 chloride at room temperature and pressure. State its structure and bonding. Okay, so silicon 4 chloride is SiCl4. Okay, it's SiCl4, and this is a period 3 chloride. Okay, that's a liquid. Okay, that's a liquid. So you guys are expecting now the chlorides of sodium, magnesium, aluminum, silicon, and phosphorus. Okay, all of them are solids except for silicon 4 chloride, which is a liquid. Okay, all of them are solids except silicon 4 chloride, which is a liquid. Okay, it is a colorless liquid. Okay, and the structure and bonding, well, it has a simple molecular structure, right? Simple molecular structure, right? And the bonds between the atoms are covalent bonds. Okay, so simple molecular structure, and you have covalent bonds. Okay, covalent bonds. Samples of magnesium chloride and phosphorus 5 chloride are added to separate beakers of cold water. Complete table 3.1. Ignore temperature changes when considering observations for these reactions. Now again, as I just mentioned, right, all the chlorides that you need to know, sodium, magnesium, aluminum, silicon, and phosphorus, all of them are white solids except for silicon, right? Silicon 4 chloride is a liquid, colorless liquid. Okay, magnesium chloride is a white solid. Phosphorus 5 chloride is also a white solid. One similarity in observation on addition to cold water. Okay, they both dissolve to make a colorless solution. They both dissolve to make a colorless solution. One difference in observation on addition to cold water, right? With magnesium chloride, okay, magnesium chloride is almost a purely ionic substance, right? So it just dissolves, right, to give us aqueous ions. It does have partial covalent characteristics. It does have partial covalent characteristics, but it's pretty much ionic, okay? So the pH of the solution is slightly below 7. It's slightly below 7, okay? But we just assume that it's approximately equal to 7. Whereas PCl5 is a covalent chloride. It undergoes hydrolysis when it reacts with water, okay? So there's a reaction with water. We have a hydrolysis reaction. We get HCl and H3PO4, right? We get HCl and H3PO4, and then we get 5HCl here, and we have 4H2O. Okay, the observation is that we get white misty fumes of HCl, okay, hydrogen chloride. Some of it remains in solution, whereas some of it is given off as vapor, right? So the observation is with magnesium chloride, there's no fumes, right? No misty fumes, right? Whereas with PCl5, you're going to see misty fumes of HCl, okay? Misty fumes. Okay, that's because of the HCl being produced. Okay, hydrogen chloride. The pH of the final solution is approximately equal to 7. Okay, it's 6.5. You can say 7 as well. Okay, so 6.5 to 7. And then with phosphorus 5 chloride, okay, you get an acidic solution, a pH of 2. State the reagent and conditions required for the formation of sodium chlorate 5 from chlorine gas. Now, if you react chlorine gas with hot aqueous sodium hydroxide, okay, if you react with hot aqueous sodium hydroxide, okay, you get a disproportionation reaction. You get a disproportionation reaction in which sodium chlorate 5 is formed. Okay, I'll write this equation down. Cl2 will react with hot aqueous sodium hydroxide to give us NaCl, NaClO3, okay, and H2O. So this guy is sodium chlorate 5. Okay, this is sodium chlorate 5. Okay. And the balanced equation for this is 3Cl2, 6NaOH, 5 NaCl, 1 NaClO3, and 3 H2O. Okay. ClO3 minus is the chlorate 5 ion. Okay. ClO3 minus is the chlorate 5 ion. Explain why the reaction C part 1 is described as a disproportionation reaction. Your answers should refer to relevant species and their oxidation numbers. Okay, so over here we can say that chlorine, okay, is oxidized. Okay, chlorine is oxidized from 0 to +5, right, in the chlorate ion, and reduced, okay, from 0 in the elemental form to -1, right? That's the chloride ion, and both of these things happen simultaneously. Okay. The next part says chlorine reacts with methane in a series of reactions to produce chloroalkanes. State the conditions required for chlorine to react with methane. So when chlorine reacts with methane, we have a free radical substitution reaction, right? This reaction takes place in the presence of UV light. Okay, so that's the essential condition for this reaction. One of the products of the reaction is dichloromethane. Okay, dichloromethane, which reacts further to produce CHCl3. Complete table 3.2 to show details of the mechanism that forms CHCl3 from CH2Cl2. The first step is initiation. Okay, in the initiation stage, the chlorine molecules undergoes homolysis or homolytic fission to form chlorine radicals. So we get chlorine radicals. The chlorine radicals react with CH2Cl2. Okay. Now what happens here is that the CH bond breaks. The CH bond breaks. Okay. We have again homolysis taking place. So we get CHCl2. Okay. One of the hydrogens break off. We're left with this radical and we get HCl. Okay. The reason chlorine bonds with the hydrogen instead of the carbon is because the HCl bond is stronger. And then the termination stage, if we want to make CHCl3, well, this CHCl2, okay, the CHCl2 can react with a chlorine radical, okay, it can react with a chlorine radical to make CHCl3, okay. Termination is when two radicals react to form a molecule, okay. There is one propagation stage missing over here, okay, there is one propagation stage missing over here. So if you were asked to write the full mechanism, you should write the second propagation reaction as well, okay. You should write the second propagation reaction as well. All right, that's missing over here. The second reaction over here would be, when the CHCl2 radical reacts with chlorine molecules to give you CHCl3 and more chlorine radicals. Okay, so once you have these CHCl2 radicals, they can react with other chlorine molecules to form the product, which is CHCl3, or the CHCl2 once made can also react with chlorine radicals. Okay, both of these reactions, this reaction and this reaction, are happening simultaneously. Once you have this radical, it can react with chlorine radicals or it can react with chlorine molecules to form this product. Okay, if a radical reacts with a molecule, we say that's propagation, so that will be our second propagation reaction. If you had to write out the mechanism in full, and if the radicals react with each other to give the product, that's termination. CHCl3 and HF are used to form CHClF2 in a substitution reaction. Construct an equation for this reaction. So we have CHCl3 reacting with HF, okay, to give us CHClF2, and then we're removing two chlorines from here. Okay, we're removing two chlorines from here, right? So those chlorines will combine with the hydrogens. Okay, those chlorines will combine with the hydrogens. So let me write this down, right? We have 2HF because we're substituting two fluorines. Okay, we're substituting two fluorines over here. And then, right, we're removing two chlorines. So we have 2H and then 2 Cl's. So we get 2 HCl. Okay, we get 2 HCl. So that would be the balanced equation. Okay, so again, two fluorines, so we need 2 HF, and the two hydrogens combined with the two chlorines that are removed. So we get 2 HCl. X is the product of the substitution reaction that occurs when CHClF2 reacts with Br2. there's only one naturally occurring isotope of fluorine, that's fluorine 19. The mass spectrum of X shows molecular ion peaks at mass to charge ratio 164, 166 and 168. Complete table 3.3 to show all the molecular ions responsible for each peak. So they said that when this guy reacts with Br2, right, this is our product. We get CF2, here we get CF2, Cl and then Br, right? CF2, Cl, Br. Now they said that the peak at 168, right, that's due to the heaviest molecular ion, right? That's the heaviest molecular ion is when you have a chlorine 37 and a chlorine 81. Now the peak at 164, would be because of CF2. Then we have a chlorine 35, that's the lighter isotope of chlorine, and a bromine 79, right? That's the lighter isotope of bromine. Again, we have to show the 1 plus charge, right? Because they're asking for molecular ions. Again, it's the cations that show up in the mass spectrum. And then at 166, the peak at 166 could be due to two different ions. Okay, one possibility is if we had a CF2, okay, we had a chlorine 37, so the heavier isotope of chlorine and the lighter isotope of bromine. Okay, so that would be Br 79. And the other possibility is if we had the lighter isotope of chlorine and the heavier isotope of bromine. Okay, both of them would give you a peak at 166. Okay, mass to charge ratio 166. So again, they're saying that the heaviest molecular ion is this one, where you have both the heavier isotopes. Okay, now if you had both the lighter isotopes, the mass would be 4 lesser, right? The mass would be 4 lesser, right? So you'd have 35 instead of 37 and then 79 instead of 81. So 2 lesser for bromine, 2 lesser for chlorine, right? And for the guy in the middle, right, at 166, if you had a chlorine 37 instead of a 35, you have an increase of 2. Or if you had an increase of 2 because of a heavier isotope of bromine, again you have an increase of 2, right? So lighter isotope of chlorine, heavier isotope of bromine. So both of these species, okay, this one and this one, right, these two molecular ions are responsible for the peak at 166. So here we have question number 4, which says V is a colorless liquid. Okay, they've given us the structure of V over here. So let's try naming this compound. Okay, here we have a 4-carbon chain. The priority should be given to the carboxylic acid, right, the carboxyl group. So we have a 4-carbon chain, so that is bute, right, 4 carbons. We have a double bond on carbon number 3, so bute 3-ene, right, bute 3-ene. And then we have a carboxylic acid group, right? We don't have to number that because it's implied that it's on carbon number 1, okay, because it'll always be at the end. So bute 3-enoic acid. V reacts with an excess of lithium aluminum hydride to form W. Draw the structure of W in the box. Now, when V reacts with lithium aluminum hydride, right, that's a reducing agent that reduces carboxylic acids and carbonyl compounds, right? Here we have a carboxylic acid, right? We have a carboxyl group. So that'll become a primary alcohol, okay? This will reduce the CO2H to a CH2OH, okay? So this will become a primary alcohol. So what do we end up getting? We have a 1, 2, 3, and then 4. Okay, the alkene will remain unchanged. Okay, alkenes can only be reduced by hydrogen and nickel as far as we're concerned. And we end up with a CH2OH. Okay, the COOH becomes a CH2OH. Identify the role of lithium aluminum hydride. It's a reducing agent. Okay, we have to use anhydrous lithium aluminum hydride. So that's lithium aluminum hydride in ether as a solvent, okay, instead of water. V reacts to form Z in a single reaction as shown in figure 4.2. Suggest the reagents and conditions needed to form Z from V. What we're doing here is converting an alkene, a carbon-carbon double bond, into a diol. Okay, so we're adding two OH groups. We're adding two OH groups in a single reaction. For this, we're going to use cold dilute acidified manganate 7. Okay, cold dilute acidified manganate 7 or cold dilute acidified potassium manganate 7. Deduce the empirical formula of Z. So Z has 1, 2, 3, 4 carbons. It has 4 carbons. It has 1 and then 2, 3. Right, we have 2 hydrogens here. We have 2 hydrogens here. We have one hydrogen here, 4. We have 2 here, 5, 6, and then 7. Okay, and then 8, right? I'll count these again: 1, 2, 3, 4, 5, 6, 7, and then 8. So we have C4H8, and then we have 4 oxygens: 1, 2, 3, and then 4. Okay, so C4H8O4, and then we can just divide all of these numbers by 2 to get the simplest ratio, which is CH2O. Complete table 4.1 to show the number of sp2 and sp3 hybridized carbon atoms that are present in a molecule of V. Okay, so again, V over here is this guy over here, right? The but2-ene oic acid, right? But2-ene oic acid. So this compound here. How many sp2 carbons do we have? Well, the carbons that have double bonds, right? This carbon, and then this carbon here, right? All three of these are sp2. Again, the hybridization is determined by the number of atoms bonded, okay? The number of atoms bonded to that carbon plus the number of lone pairs, okay? Plus the number of lone pairs. Now, for the carbons that have double bonds, this carbon is bonded to 3 atoms. You have 2 hydrogens, and then it's bonded to another carbon, right? So it's bonded to 3 atoms. So if it's bonded to 3 atoms, there's no lone pairs, right? If this total is 3, then we have sp2 hybridization, right? If it's 4, we have sp3, okay? And then if it's 2, then it's sp, right? If it's 2, then it's sp hybridization. So this double bonded carbon, sp2, this carbon is bonded to 3 atoms. You have a hydrogen, this, and then this carbon. And this guy is also bonded to 3 atoms. Okay, this carbon is also bonded to 3 atoms. So these are all sp2, okay? I'll underline these. Okay, these are all sp2. So we have 3 sp2 carbons, and then this one over here is sp3 because it's bonded to 4 atoms, right? It's bonded to 4 atoms. So this is sp3. We have 1 sp3 carbon. Q contains the elements carbon, hydrogen, and oxygen only. It is a saturated molecule, okay? It is a saturated molecule with no branching in its carbon backbone, okay? There's no branching, so there's no branching. It contains only one functional group. The relative molecular mass of Q is 88, okay? The relative molecular mass is 88. No effervescence is seen when reacted with sodium carbonate, so it's not an acid, right? It's not a carboxylic acid. We know it's not a carboxylic acid because it's saturated. Carboxylic acids are unsaturated because they have a double bond, right? Effervescence is seen when sodium is added to Q. That means we do have an OH group. And if it's not an acid, okay, if it's not acid, that means that it must be an alcohol. And Q reacts with alkaline aqueous iodine to form a yellow precipitate, okay? Reacts with alkaline aqueous iodine to form a yellow precipitate. So that's the iodoform reaction, right? The yellow precipitate that we get is triiodomethane, okay, CHI3. So if it reacts with alkaline aqueous iodine, it means that we have, okay, it means that we have a CH3 CHOH group, right? We have a CH3 CHOH group, right? The iodoform reaction is only possible if you either have the CH3 CHOH group or we have a CH3CO group. Okay, we have a CH3CO group. So either we have an alcohol or a carbonyl compound. We can't have a CH3CO because it's saturated. So that option's out, right? So it must be a CH3 CHOH group. So we have CH3. Okay, then we have a CHOH. Okay, so CHOH. And then how many more carbon atoms do we have? The molecular mass is 88. So here we have a mass of CH3 is 15, right? We have 1 carbon, 2 carbons, 24 plus 3, right? That is 27. So 15 plus 12, 27. The OH is 17, so that's 44 plus 1, that's 45. Okay, so this CH3CHOH, okay, the CH3CHOH has a mass of 45, right? Has a mass of 45. The total mass is 88, so we're left with 88 minus 45, which is 43. And a mass of 43 means you have 3 carbons, that's 36, and then H7. Okay, so that's CH2, CH2, CH3. Okay, so this compound is pentan 2-ol. Okay, this compound is pentan 2-ol. 5 carbon alcohol, then OH group and carbon number 2. So this will give you a positive test with the iodoform reaction. right? It will react with sodium metal because it has an OH group. It has an MR of 88, and it won't react with sodium carbonate because it's not an acid, and it's a straight chain compound that's saturated. So here we have question number 5. It says molecule M is present in petrol, a fuel used in cars. M is a saturated non-cyclic hydrocarbon. M contains 8 carbon atoms. Construct an equation for the complete combustion of M. Okay, so M is C8H18, right? That's octane. Okay, octane. Okay. When octane is combusted, okay, for complete combustion, we get carbon dioxide and H2O. Okay. To balance this, we're just going to say 1 mole of octane here. Okay, we're going to have 1 mole of octane here. That means we'll have 8 carbon atoms, so that's 8 CO2. We have 18 hydrogen atoms, so that's 9 H2O. And then we have 8 times 2, that's 16, plus 9, so that's 25 oxygens. So that would be 12.5 O2. Okay, so you can write it as a decimal, you can write it as 25 over 2. Okay, you can multiply everything by 2 if you want to write in whole numbers. Anything's fine. Okay, decimals, fractions, whole numbers. Okay, as long as it's balanced. Describe how the composition of products differs when incomplete combustion of M occurs. So how does the composition differ? So if you have incomplete combustion, right, you're going to have carbon monoxide and carbon can be present, right? So we can say that more carbon monoxide, okay, and carbon will be present, right? Right, if we have lesser oxygen available, you're going to make carbon monoxide, and if you have very little oxygen, then you're going to make carbon, right, or soot. And of course, we're also going to have lesser carbon dioxide, right, and lesser CO2 will be present. Okay, so they're saying we have to compare the composition of the products. Okay, we have to compare. They're saying how does it differ, so we have to compare the composition of the products. Okay, so lesser CO2 will be present, okay, as well. When petrol is burned in an internal combustion engine, oxides of nitrogen are released into the atmosphere. Oxides of nitrogen are responsible for the formation of acid rain. Suggest the conditions required for the production of oxides of nitrogen during combustion of M in an internal combustion engine. Use an appropriate equation in your answer. In order for oxides of nitrogen to be produced, obviously you're going to have nitrogen gas present, right? Nitrogen gas will be present. It's going to react with oxygen. Okay? It's going to react with oxygen to produce. Okay? Nitrogen gas will react with oxygen gas to produce oxides of nitrogen. So you can have nitrogen dioxide being produced or nitrogen monoxide. We'll just go with nitrogen monoxide here. And then this reaction is only possible. So this reaction is only possible at the high temperatures present in a combustion engine, right? So we need a high temperature. Okay? High temperature because we have a nitrogen-nitrogen triple bond. Okay, that's not very easy to break. We have a nitrogen-nitrogen triple bond. That's not very easy to break, but the high temperatures provide the activation energy needed for the reaction. Okay, you also have high pressure in a car engine. Okay, so we have high temperatures plus high pressure. Describe how acid rain is formed in the atmosphere in the presence of oxides of nitrogen and sulfur dioxide. Identify the role of the oxides of nitrogen in this process. Include all relevant equations. Okay, so the formation of acid rain can be catalyzed by nitrogen monoxide or nitrogen dioxide. Okay, we look at nitrogen monoxide as a catalyst because that's what we showed forming in the previous part. When nitrogen monoxide is a catalyst, nitrogen monoxide can react with air in the atmosphere to form nitrogen dioxide, okay, to form nitrogen dioxide, and then nitrogen dioxide can react with sulfur dioxide to form sulfur trioxide, and we regenerate the nitrogen monoxide, right? So what we have here is nitrogen monoxide being used in the first step, reacting in the first step, and then regenerated in the second step. The overall equation for this reaction, okay, the overall equation for this reaction is SO2 plus half O2 gives us SO3. Okay, this equation is the equation for the formation of sulfur trioxide, right, from sulfur dioxide. This can only happen in the presence of a catalyst. Otherwise, this reaction has a very high activation energy, right? We need a catalyst for this reaction. Either vanadium 5 oxide in the contact process or oxides of nitrogen in the atmosphere. If you showed nitrogen dioxide as a catalyst, you show NO2 as a catalyst, you can just switch the two equations. Okay, switch the two equations. This will be the first equation, and then this would the first equation here will be the second equation. Okay, so both NO and NO2 can catalyze this reaction. Okay, and then we have to show the formation of acid rain. Okay, we'll show the formation of acid rain. The sulfur trioxide, right? When rain falls, combines with water to form sulfuric acid. Okay, so we get acid rain. So we get acid rain. State one other type of air pollution that is caused by the production of oxides of nitrogen in an internal combustion engine. Oxides of nitrogen also contribute to photochemical smog. Okay. Photochemical smog. Biodiesel T is a fuel made from vegetable oil R. Figure 5.1 shows the production of T from R in a two-step process. In step 1, all three ester groups in R react. Suggest a suitable reagent and conditions for step 1. So in step 1, what we're doing is we're making this carboxylic acid from this ester. So in step 1, we're hydrolyzing the ester, right? This is hydrolysis of esters. So what you're doing here is you're breaking the ester linkage, right? You're hydrolyzing the ester linkage. So the bond between the C double bond O and the oxygen, right? So you end up making this guy, right? This guy becomes a carboxylic acid, right? This, right? This is what results in the formation of the carboxylic acid, right? And we also get this triol, right? We get this triol, CH2OH, CHOH, CH2OH. Okay, so these guys become alcohol groups. Okay, these guys become alcohol groups, and then these guys over here become carboxylic acids. Okay, so this is acidic hydrolysis. The reagent for this is dilute HCl. Okay, dilute HCl and heat. Okay, dilute HCl and heat. Draw the structural formula of J in the box in figure 5.1. So the other compound that we're getting here is the CH2 becomes a CH2OH. So we get CH2OH. We have a CHOH, and then we have a CH2OH, right? Again, these guys all become hydroxyl groups, right? You do not have to draw it like this. You can give the skeletal formula, you can give the structural formula, any valid structure. I've just drawn it the way they've given it. Now in step 2, we can react this compound L with compound G in the presence of concentrated sulfuric acid to make compound T. So again, you're making an ester. Okay, again, you're making an ester here, right? We have a COOC, right? So this carboxylic acid is converted to an ester. And in this case, compound G is methanol, right? Because this is the alcohol part. This is the alcohol part. So this is CH3OH. So compound G is CH3OH, right? The reaction is a condensation or esterification reaction, okay? So the type of reaction here is condensation. So the type of reaction is condensation. We have to name organic reagent G, that was methanol. Okay, that's CH3OH. Okay, name it. And then L is called decanoic acid. Use systematic nomenclature to deduce the name of T. Okay, so this carboxylic acid is a 10 carbon acid, right? L is decanoic acid. Okay, this L is decanoic acid. So if you had to name the ester, right? For the ester, we have the alcohol name first, so that would be methyl, and then decanoate, right? That's the acid part of the ester. Methyl decanoate, right? That's compound T. The name of compound T is methyl decanoate.